Okay, right now we're going to talk about what it means to be an exponential function. So, on your note-taking guides, this is page 11. We're going to take those out. So we have done a little bit with exponential functions before. We know that they are curved. What is it? What is an exponential function? Well, an exponential function is anything that is of the form a times b to the x power, where a is not equal to 0, and we noticed in Decimus the other day that b is going to be greater than 0 but not equal to 1. Because otherwise that just kind of makes, it makes a function where you're multiplying by 1 every time, which is just a horizontal line. So this is what it's going to look like. Hopefully, after doing Decimus activity for 2 days, you have some kind of idea what those look like. But the big thing is it's exponential because x is in the exponent. So when we're putting an x, we're going to be putting it in the exponent. How can we tell if data is exponential? So basically, exponential functions have this thing called a multiplier. So to get the next value, you multiply by a number. So if we want to check and see if data is exponential, it is going to have what we call a common ratio. And what I mean by that is, if you divide y values, a ratio is when you divide, you're going to get the same number. And you always want to take a value and then divide it by the previous value. So let's take a look at the U.S. population problem. So first I'm just going to verify that the x interval is the same and it's going up by 10, so that's good. And then I'm going to start to divide some y values. So 5.3 divided by 2.9, that first ratio, that should be 3.9. Is 1.36. Alright, now we're going to move to the next y value, 7.2, and we're going to divide it by the previous. And I get the same thing almost. Okay. Let's check some more. 9.6 divided by 7.2. 1.33. Alright, I'm going to check some more of these, and if they're all in the ballpark, then I think that we're going to decide it is exponential. Remember, this is real data, so it's not perfect. 1.34. Oops. I did that wrong. 23.2 divided by 17.1. 1.35. I'm doing some random down low. 1.3. Okay. I am going to then give some numeric justification. I could do more ratios if I want, but the multiplier is anywhere, I'm going to say like from 1.3 to 1.4-ish, okay, because this data is real data. And so this is exponential. This is exponential. I found that the ratio, when I divided the y values, I got about 1.3 to 1.4-ish each time. So my answer would be yes. Here's my numeric justification. And then this would be the multiplier. Let's check the next one. So I'm going to do 8 divided by 2, and I get a 4. 21 over 8 is definitely not 4. 38 over 21. Whoa. Alright, now, these aren't even close. Up here, I mean, I had some numbers that were between 1.3 to 1.4, but we're a whole number off each time. So this is enough information to say that this is not exponential. And I'm going to write the ratio is not common. It's not the same number or constant. Okay. So, Mrs. McDonald's AP Stat students currently study for an average of 6 hours per week. After spring break, they will be reviewing to take the AP Statistics test. They will have 5 weeks to study and plan to double the amount they study every week, that should be, until the exam. Fill in the chart below and then graph. So it's filled in for you. I'm just supposed to make sense of this, okay? 6 times 2 is 12. Right? 24 divided by 12 is 2. 48 divided by 24 is 2. Okay, so all of these, now this is what I said in the problem though. 96 divided by 48, I take a y value and divide always by the previous y value. Okay, this is exponential. And what are these being multiplied by? In other words, what are you going to multiply to get to the next y value? Well, we're multiplying by 2 each time. So the multiplier, or the common ratio or constant ratio, is equal to 2. Okay. So let's graph this and see what happens. So we have 0, 6. So, I don't know, maybe down right here. 1, 12. 2, 24, well, let's see, that would be 30, so I'm going to put 24 right there. 3, 48. 4, 96. 5, 192. So you can see that at first there's not a lot of growth, but then exponential, because you're multiplying, not adding, it gets rather large. So we're going to work on this a little bit more in a minute, but can I write an equation for this graph? Well, if you remember from the last couple days when we've done some activities, going back, we learned that A was our y-intercept. In other words, it was our starting value. So in this problem, if I go ahead now to this problem, where is my starting value? Where's my starting y value, or my y-intercept? And it's right here. It's 6. So how am I getting the y values? Well, y equals, I'm starting at 6, and I'm multiplying by 2 every time. So I did 6 times 2, and then times 2 again, times 2 again, times 2 again, times 2 again. Repeated multiplication we call an exponent. So if I wanted to figure out, again, this first value right here was 6 times 2 one time, right? Because it's 12. This y value, the 24. I did 6 times 2, which is 12, and then I did times 2 again. Isn't that 6 times 2 squared? I did 6 times 2 times 2 times 2. That's 6 times 2 cubed. Notice, that's 3, and the 3 is ending up in the power of 2. So, in general, for x, I can write 6 times 2 to the x power. And we're going to get into more specifics in the second video about what those things stand for.